Hello, good evening all. Hello, good evening all.
Good evening, sir.
Yeah, so thank you for joining this session. So I actually had to postpone the Friday session to today because of a medical emergency at home. So yeah, so thanks for joining this session. Uh, so in this session we are going to discuss problems related to the course content for week 6, which is basically 2-degree freedom systems. So before we get started, are there any questions related to so that or doubts that you have related to the course content for this week? Yes, uh, Mr. Amit has a doubt. So yeah,
Sir, I have tried the assignment 6 very hard, but
okay,
some of the questions, even there is no reference made in the video lecture, sir.
okay,
So, so that is why I'm finding to solve the question with full confidence, sir. There are at least three questions in the assignment 6, sir.
okay. Uh, so yeah, so I am just opening that assignment. So let me just share. Yeah, so are you able to see my screen?
Yes, sir.
Yes, sir.
Okay. So which can you tell me like which problem you are
Uh,
referring to?
Sir, would you please scroll down, sir?
Yeah. So
Sir, yes, let me, sir, tell you the question number, sir.
mhm.
Sir, question number 5 and 7, in which we have to calculate first the mode shape and then the natural frequency, sir. So, sir, I
Mhm.
couldn't understand what is mean by this matrix form, sir. 1, 1.5, x1, x2, sir. Because sir has not discussed this type of format in his video lecture, sir.
Okay. Uh, See, I think this x1, x2 is basically this. Um, See, you can find an eigenvector. So eigenvalues and eigenvectors, right? For this. So for like for the 2-degree of freedom system, so that means the natural frequency and mode shapes. So, so natural frequencies are like analogous to eigenvalues and mode shapes are analogous to eigenvectors. So, so you can write the mode shape or whatever I like using the concept of eigenvectors. You can like you similarly apply that concept and find out the eigenvector or mode shape. So it's basically so mode shape here. So do you understand what do you mean by mode shape?
Sir, mode shape is somewhat clear, but this eigenvectors I didn't remember, sir. Can we take a similar example in today's live session, sir?
Yeah, yeah. So I am going to actually start like from scratch, like from very basic because this is like somewhat when you move to like multi-degree of freedom systems, then the approach actually is uh, like there is some this concept of eigenvalues or eigenvectors that we can so we'll go through that, so hopefully some of those doubts will get cleared through that.
Okay, sir.
So mode shape essentially means that so when your system is oscillating at its natural frequency, so because it has like so if the system is a 2-degree of freedom system, then it will have two natural frequencies, right? And so for when it is oscillating at its natural frequency, So x1 and x2 will be in a certain proportion. So they will, so the amplitudes will be in a certain ratio. So let us say if the, here, so here it is like somewhat simple to visualize. Like let us say if there are, like suppose there are two blocks of masses, like same mass, and so one natural frequency you can imagine is like if you stretch the masses equally on both sides, let us say, and release them, so then that will be one natural frequency, right? So that that is one natural frequency, and then in that case, so then the masses will be moving in opposite directions, but with, let us say, equal displacements and opposite directions. So then you can express the mode shape as 1 minus 1. Or if the uh, let us say masses are, uh, if the system is just translating, so then x1 and x2, and in that case, let us say the, so there is no oscillation as such. So then, and if they move in such a way that the spring does not stretch at all, so then both the displacements have to be equal, x1 and x2 has to be equal. So then you can write the eigenvectors 1 1 because they are like equal. Whereas if when they are equal and opposite, then you write it as 1 minus 1. So that's like the other like mode shape. So so do you get the idea somewhat, like what I meant?
Yes, sir. More or less, I got the idea that actually it represents the relationship between the amplitudes at the natural frequency.
Right.
It shows the actual dynamic profile of the structure.
Yeah. So basically the amplitudes will be in a certain, like the displacement will be in certain, like let us say equal or opposite, equal and opposite, or then it's like 1 minus 1, and or if they are in certain ratio depending on the natural frequency. It all it basically depends on the mass and stiffness properties in the system. So
Yes.
yeah, so yeah, so
Sir,
we
actually,
yes,
my issue was that the sir has explained the meaning of mode shape in the video lecture,
okay,
but he has not referred this type of notation which we see in these questions, sir. So I am
okay,
feeling uncomfortable with this x1 is equal to 1, 1.5 and x2 is equal to 1. So that
okay,
is the issue, sir.
okay. So what I would suggest is like we will first go through whatever today's problems also, and I would also encourage you to refer to this textbook on mechanical vibrations by S.S. Rao. So that has
Okay, sir.
a like a good description of like this thing. Like it is a good book to refer. So I have been referring to that book since a long time. So that is a, like I feel that that is a good book. So I think, and if you still don't understand, then we can maybe discuss in the next session or something, like, or you
Okay,
can
sir.
email me your questions, like if you have any.
Sure, sir.
Yeah. So and one, like one point which I actually forgot to mention. So I received a couple of emails since the last session, but because of the ongoing medical crisis at my home, so I was not able to respond them. But yeah, as soon as I get time, I will respond to them. So yeah, sure. Uh, any other doubts like related to the assignments that you had? Any other question that you
Yeah,
thought
sir.
of?
In question number 4 and 5,
Hmm.
when there are two masses and they are coupled by a single spring, sir.
Yes,
So,
yes.
sir, I am unable to draw the free body diagram for the forces acting on it
You are
because
unable.
what we have done in the video lecture, we
Hmm.
have at least two springs.
Yeah.
But in this question, there is two masses, and both are connected by a single spring only, and none of the body is fixed to the vertical wall, sir.
Yeah, so that's not a problem actually. So I mean, if I actually give you further hints, then I am actually kind of indirectly telling you the answer. But basically, the I what I will just say that the spring force actually depends on the relative displacement of the masses, right?
Yes, sir,
And
that is okay, sir.
if
But
you
what, yeah, sir, I am finding problem to draw the forces acting on M2 only, sir.
yeah, for whichever
Be-
mass as such.
Because from my calculation, both the forces acting on the M2 is in the same direction, sir. At least one force should be opposite to the first one, sir.
What do
So
you
there
mean
are two
by
forces, sir. In this question, we have a second mass M2, sir.
yes?
Okay, so inertia force M2x2 double dot is acting from right to left, and the spring force K delta x also acting from right to left, sir.
Mm-hmm. Okay.
So how this mass M2 will get balanced, sir? At least they should be opposite in direction, sir.
See, you can basically assume a certain direction of the spring force based on the whatever relative
Yes, sir.
displacement,
Yes,
and then that direction should be consistent for both the masses, like right. So, uh, in the sense like if the spring is undergoing compression or if it is in tension or whatever, so that should be consistent for both the masses whenever you draw the free
yes,
body
sir.
diagram. So that
Yes, sir.
uh, is one thing. And yeah, so I think I further I think I should not further tell you like give you more hints because then I would like actually indirectly give you the answer in itself, I think.
Okay, sir. I will try again, and
But
if there is
yeah,
still problem, I will mail you, sir.
sure, yeah, okay. Anything else like any conceptual doubt that you may have? Yes. So Mr. Prashant has a question.
Yes, sir. So mostly in 2 degree of freedom systems, mostly the problems are seen on spring mass system.
Right,
But in actually in the book of Ra or other books, there are many problems on torsional vibrational system or double pendulum like system.
right.
So
Okay.
will there be any questions in the final exam on this torsional vibration or double pendulum?
Uh,
Because these two systems are again 2 degree of systems.
yeah, so if there are problems like that, so I mean, it may be there. I mean, I cannot say exactly because I'm not the person who sets the exam question paper as such. But what I can say is
Okay.
that may whatever the type of system it may be,
Okay.
essentially we have to just come up with a differential like a system of differential equations and for like each degree of freedom. Let us say if one degree of freedom is like translation and other is rotation or both rotation, like let us say double pendulum or whatever, so then there are like there is like translation plus rotation or whatever, so that kind of system. So whatever the system is, we should basically be able to draw the free body diagram and using that write the equations of motion. And so mainly that would be the I mean, so whatever the system is, basically we should be able to draw the free body diagram. So be it a spring
Right,
mass
right.
system or
We
whatever.
need to find the natural frequencies of that systems.
Yeah, so once you
It's,
get the differential equation, so let us say if in
yeah.
case of a pendulum or that case, so then the to find the natural frequency of the pendulum or whatever, so generally we do some simplifying assumptions like the angle of like oscillation, like it is small angles of oscillation. So then using that we simplify the differential equation. So such kind of simplifying approximations can be done like depending on their validity for that system, like for depending on the practical, like the context. So yeah, so we can so given a certain system, we should be able to basically draw the free body diagram, then write down the equations of motion, and then once we derive that, then we can solve those equations of motion. Or so to solve, or if you want to get the natural frequency, then we need to basically do a like a analysis of eigenvalues and eigenvectors. So in that sense, so for that
Okay,
system,
sir.
whatever.
Okay, right, right. Means mostly the problems are on spring mass system, so we have to prepare basically for that. And mostly the questions are asked from assignments, assignment basic question in final exam.
Yeah, you can
So
expect
that's
mostly
better.
related to that. Yeah, so largely
Mhm.
you can expect related to that, but at the same time, I think you must be aware, like if there is like
Right,
if you
right. We can,
let us say
yes, sir.
if you come across a system which is not like spring mass, but there is like certain element which is like represents some kind of stiffness. So it may be torsional stiffness or whatever, or that kind of.
Double
So
pendulum.
you can
Double
model. You
pendulum.
should be able to basically model that and write the differential equation. So yeah, so from the exam point of view, so you may expect largely related to that. Uh, Other than that, I think I cannot say much about the exams as such.
Right. Okay, sir. Okay.
Yeah.
One more doubt is there, sir. So mostly the questions are asked in assignments are of one point only, and their answers are very lengthy. So for 100 marks exam in final examination,
Hmm.
so is the time sufficient? Will the time sufficient for that? Or the questions may ask for 2 points and 50 questions may ask in final exam, like that?
Uh,
Because for 1 point means the time will not be sufficient if they ask such type of question for 1 point.
yeah, I think it should be sufficient. Like, uh, so if the exam is for 100 marks and like 100 marks, so then so they will set the question paper so that you will like most of the like learners will be able to complete the exam, attempt the exam in within that given time. Let us say, so they give 3 hours, right? Or how much like time?
Right, it is of 3 hours and it
Three
is a
hours,
100 question, 100 marks exam.
100
So
marks.
according to the this marking system, there will be 100 points for 100 marks, 100 questions. Means one question is of 1 point.
Yeah, so
So
there
in
may
3 hours, 100 question, such type of 100 question solving is very
no,
difficult.
it may not be like 100 questions in 100 mark, 100 like 100 marks, like so that I don't think there will be 100 questions in 3 hours. So there may be lesser number of questions, but they are like likely to be mostly multiple choice, or if not multiple choice, so then you can type your answer somewhere like that, like type your answer in a text box or like that kind of thing. So it's a computer based exam only, right?
Right, right. Okay.
Yeah,
Let us
so
see what happens in final exam.
yeah, so I
Okay,
am
sir.
also not sure exactly because I have not been through an NPTEL course like exam as such, but yeah, so it won't be like I don't think it will be like 100 questions in 3 hours. Like that is not even the case with exams like GATE or whatever they.
Right, right. So they may ask big questions for 2 points like that,
Yeah,
and
yeah.
simple question for 1 point.
Yes, yes.
Hmm. Okay.
Yeah, so
Okay, sir.
because
Okay.
this is like just one like a weekly assignment where there is no time limit as such, like for a particular solving like this. Let us say if you have 10 questions in this assignment, so then there is no like time limit for you to attempt the assignment, right? So then So you should not like take this like whether like this much length question is for 1 point or whatever. So that will they I think that they will set it wisely as per the time requirement. So the weightage or like marks allotted to the question will definitely depend on the time required to solve it. Yeah.
Right, sir. Right. Okay.
Any other queries?
No, sir, not from my side.
Okay. Anyone else has any question? If not, then shall we start with the problem solving? Yeah. Okay. So I'm just sharing my screen now. So are you able to see my screen? Yeah. Okay. So yeah, so let us get started with the problem solving session as such. So what I have like thought that because this concept of this multi-degree of freedom systems is like slightly different, so then I thought like let us solve a simple problem, simple or whatever simple looking problem at least, which uh, from where we can. So I'll also establish whatever notation or whatever with whatever I am familiar with, and so my method may be slightly different from what you may have come across in your like video lectures. So if you get confused anywhere, so just let me know. So we can just clarify whatever. So I'll be using slightly possibly different notation from which you may like commonly come across in textbooks, but hopefully that I'll try to clarify as we go along. So so we have this 2 degree of freedom system here which is given, and what we have to do is to derive the equations of motion for this system. So we have like two masses m1 and m2 which are connected together by springs k1 k2 like with stiffness k1 k2, and viscous dampers with damping coefficients c1 and c2, and they are connected to this k2 and c2. They are basically connected to a base. So this base, it can be a movable base which for which let us say the displacement e of t is let us say known or prescribed. So the displacement y1 and y2, so this is the positive direction for the positive y direction which I have indicated, and let us say e of t is already known or prescribed. So what we will assume is that y is whichever like y1 or y2 whichever, so they are with respect to the equilibrium position. So then we don't have to consider the weight. So basically y1 and y2 are with respect to their respective equilibrium positions. So we will make a use of this fact while deriving the differential equations and just simply neglect the effect of gravity, because so we have discussed that, right? So when we derive the write the equations of motion in terms of the displacement with respect to equilibrium position, so then the static deflection and the gravity, basically they are kind of just get nullified in that sense. So then, yeah, so then we will draw the free body diagram now for this each of the masses, right? So so let's first draw the free body diagram for mass m1. So there will be two uh, external forces acting on this. So apart from gravity, so which we just I mentioned that we will neglect it because we are considering the displacement with respect to equilibrium position. So in this, let us say we assume for the time being just that y1 is greater than y2 as such, like, so so with what, why will we assume that y1 is greater than y2 is, let us say, this is just for the sake of like just an assumption, so that because y1 is greater than y2, so then we can expect that the spring k1 will be in tension. So the spring force in the k1 spring, so that will be tensile in nature, right? So what will be the expression for the spring force in, like, force in the spring k1, which has a stiffness k1? What will be the expression for the spring force? So for the spring, let us say I call fs1. Yeah, so it will be k1 into y1 minus y2. And similarly for the damper, so it will be c1 into y1 dot minus y2 dot. And now let's also draw the free body diagram for m2. So there will be four external forces acting on m2. One thing which you may have noticed till now, so I generally never use this concept of pseudo forces. So that is not generally needed. Uh, so I think some people refer to things like inertial force or whatever, I don't know. So but uh, basically generally that is not needed as such. If you can just write the equations of motion in an inertial frame of reference and then write the equations of motion. So so these will be the equal and opposite forces by in the spring K1 and damper C1. Similarly, there will be other forces because of this, let us say we assume that the spring K2 is also in tension. So then the spring force in K2 that will also, let us say, be tensile. So then, so what will be the expression for the force in the spring K2? So any idea what will be the force in the spring? No, it will not be only Y2, because let us say the base is also moving. Base is not fixed, let us say. It is moving with, like, it has a displacement. Yeah, so it is K2 into Y2 minus E, right? And C2 Y2 dot minus E dot. So those will be the forces acting on the mass M2. And here we assume that or E dot is already prescribed and known with respect to time. So then that is not a separate variable as such. So then now since we have completed the free body diagram now, so we can derive the equations of motion now. So we will apply Newton's second law to each mass. So M1 Y1 double dot will be the net external force acting on the mass M1, which will be the spring force and the damper force, but both are in downward direction. So we will write it as minus K1 Y1 minus Y2 minus C1 C1 Y1 dot minus Y2 dot, and the equation of motion for the mass M2. So we can similarly write it as M2 Y2 double dot is minus K2Y2 minus E minus C2 into Y2 dot minus E dot. Right, so then these are the two main equations of motion here. So what we can do is like we can rearrange the terms and take some of the terms which are like functions of y1 and y2, like those terms on left hand side, and retain the terms which contain like e and its derivatives on the right hand side, because it is already known. So it is analogous to applying an external forcing, which is because of the motion of the base. So there will be some force that is being transmitted to the system through that motion of base through the spring and damper. So that those terms will represent that force. So if we rearrange the terms, so let us say, so m1 y1 double dot plus k1 y1 minus k1 y2 plus c1 y1 dot minus c1 y2 dot is equal to 0, and m2 y2 double dot minus k1 y1 plus k1 y2 plus k2 y2 minus c1 y1 dot plus c1 y2 dot plus c2 y2 dot will be equal to k2 plus c2 e dot. So hopefully I have not missed any term. Yes.
Sir, one doubt is there. If the base is also moving,
Yeah.
isn't this is 3 degree of freedom system now, or
No, if
it
the
remains 2 degree of freedom?
no, that's why I told you that if the motion of the base is already known, So then that is not a degree of freedom. So if that is already, so if that also becomes a variable, then it becomes a 3 degree of freedom system. So if it is
Okay,
already
okay.
known, then only the variables are y1 and y2.
Okay, means displacement is known. It.
Yeah, yeah. So displacement is known. Let us say it is some sinusoidal function or some sine or cos function or something, whatever. That function is known, let us say.
Okay, sir. Okay.
So then that does not become a degree of freedom. Yeah. So one thing is that in this particular concept of multi-degree of freedom system, so there is a lot of algebra. So here and like there will be a lot of like equations and terms of here and there. So just we have to be careful that we don't miss out anything. Now we have these two set of differential equations, so we can write it in matrix form now. So then we can rearrange it and write it as now we can also like write the damper like matrix for the damping. So this is like the equation in matrix form. Now what we can like we can designate uh, like each of them as a like different like separate matrix. So like let us say this matrix we write it as matrix M, capital M. This we designate it as capital K, matrix capital K. This as capital C matrix, and this is like the force matrix. And the we write this matrix as Y, or like vector Y as for that matter. So So y1 and y2 is basically this. So it's basically this vector. So this thing is basically the y vector y1, which is the set of y1 and y2. So this will be y double dot and this will be y1 y dot basically vector. So we can write it in a more compact matrix. In a matrix form, we can like write the whole system as so when I'm underlining this letters M, C, and K, that I mean it that those are like square matrices. Whereas when I am kind of placing a curled some symbol below the, let us say, Y, I mean that that is like basically a vector. So when I am underlining it as a straight line, so I mean it that it is a square matrix. Yeah, so this is basically the entire equation in a compact matrix form. So this is very similar to the equation of motion for a single degree of freedom system, like forced vibrations of a single degree of freedom system. So it's very similar to that. Uh, Now the only difference as such, so the only difference as such is in terms of that this is a matrix equation and this is like a uh, for a single degree of freedom system, it's a scalar equation. So that's essentially the only difference, but the equation is like very similar and analogous in form. So we can use a similar method to solve it. So again, like for forced vibrations, so we have the solution to this equation will have two parts, right? So if y is the solution to this, so it will be, so how do we find the solution in this case, like for forced vibrations? How do you think we find out the solution in this case?
Sir, y is equal to uh, y1 e raised to power st.
Yeah, so that is like yeah, so that is right. You're right, but before that, so basically solution has broadly two parts, right? So it is solution to the uh, homogeneous differential equation where this f vector is not present. So then that is the solution, like basically the free vibrations problem, solution for the free vibration problem. So let us call it as YH. So solution to the homogeneous differential equation or complementary function. and then the particular integral or particular solution, so which is yp. So the nature of yp will depend on the nature of f, whereas the yh will depend on the nature of the yh will depend on the nature of the mass and stiffness and damping also. So we can use the usual method to solve this differential equation. So let us first start with the homogeneous differential equation part. So where we write it as my double dot plus cy dot plus ky is 0. So that is the homogeneous differential equation. So so then as you suggested, so we can solve it using by substituting, let us say y is some vector v, let us say, just to avoid confusion, like we will just use the letter v e to the power, let us say, lambda t. So where v is another vector, so then y dot will be v. So and let us say v is a constant, uh, so then that will not change with time. So so y dot will be basically v into lambda e to the power lambda t, and y double dot will be lambda square v e to the power lambda t. So y dot is basically lambda v e to the power lambda t, which is same as lambda y, and this is same as lambda square y vector. Sorry. Oh. So now we can, using this information, we can just rewrite now our equation as, so this is the kind of equation that we get. So which is very similar to the kind of equation that we get in a single degree of freedom system. But here it's a matrix equation. And we know that e to the power lambda t is never 0 for any real value of time t. So the equation that the this thing on the left hand side is 0 means that, so e to the power lambda t is never 0, so which means that lambda square m plus lambda c plus k matrix, so that into v is 0. So then we can just say that this is 0. So the trivial solution to this matrix equation that this thing is 0 is that when v vector itself is a 0 vector, but if v is a 0 vector, then will also be a 0 vector, then that means that the system is not moving at all. So but that is not the kind of solution that we are looking for. So we have to look for a non-trivial solution where v is not equal to 0. Now for this matrix equation, it's of the form like, let us say, ax equal to 0 form. So what will be the next step, like for this to have a non-trivial solution? What is the condition for that? Let us say if you have a matrix equation of the form, let us say ax is equal to 0, and for a non-trivial solution, so when I say non-trivial means non-zero, where both terms, like not all terms in the vector x are 0. So any idea what is the condition for this to be true? So anyone has any idea? Okay. Anyone else? Any idea? So basically, for this matrix equation to have a non-trivial solution, we need to have determinant of the matrix A to be 0. So we'll apply the same concept here, that determinant of this matrix lambda square m plus lambda c plus k. So this equation that this determinant is 0 is actually same as the characteristic equation. This is like analogous to the characteristic equation that we get for a single degree of freedom system. So whatever we are familiar with, like the characteristic equation, so based on which we get, the nature, like, for a single degree of freedom system, whether the system is like what is the uh, like the nature of the system. So we get the characteristic equation depending on the mass, stiffness, and damping values. So we find out what are the two roots of that characteristic equation, which are basically the two natural frequencies here in this case. And based on the roots of the nature of the roots of the characteristic equation, so if it has, so for a single degree of freedom system, if the characteristic equation has uh, real roots, two real roots, then the system was like over damped. Then if the system has, like, the characteristic equation has uh, let us say two equal roots, so then it is critically damped. Or if it has two complex roots, so then that means that the system is under damped, right? So it's the same or similar type of concept here. So are you able to follow whatever we have like done so far? So any doubts related to, so whatever we have covered so far, any doubts on that? If not, then we will just proceed with the method. So we know the matrices M, K, and C for any given system, and so we can write down the overall, like, so we can write the equation for this determinant is equal to 0. So we can write down the expression for the determinant. So we are basically trying to combine this, like basically add the matrices lambda square into M plus lambda C plus K matrix to get the overall matrix, and then writing down basically the expression for the determinant, and then equate it to 0 to get the roots for or basically the solution for lambda. So this is same as what you usually do, that in you are given any 2 degree of 2 second order ordinary differential equation, we substitute like y some y1 a to the power st, substitute in the differential equation and find out the roots for the characteristic equation in terms of s. So, and depending on the nature of roots, which I just talked about. So it's very similar to that, but it's in a slightly, in the matrix algebra kind of way. So that's why it's slightly different and slightly more complicated. So the algebra, it's basically an complicated in terms of algebra. Conceptually, it's like very similar. So this is the basically the the overall matrix, and then this is the determinant, and then we can expand this determinant further to and equate it to 0 to get the so basically get the characteristic equation. So if you kind of expand this determinant, then you will basically notice that it is a fourth order equation in terms of lambda. So it will have like terms like lambda to the power 4 and other terms. So it will be a equation which has four roots. So so is everyone able to follow whatever I'm like whatever we are doing? Okay. What about the others? Are you able to follow? So if you have any doubts, so just let me know, or else we can proceed. Okay. Okay. Fine. So basically, if we so there is a lot of algebra involved in it. So that's why like it takes time to write down everything. But conceptually, it's like basically the same thing that we do for a single degree of freedom system. So it will have like if you kind of multiply the terms in the determinant, so it's a now it's just a 2 by 2 matrix, and its determinant, you know, it like it's easy to find out. So it's basically lambda square m1 plus lambda c1 plus k1 into this term, basically lambda square m2 plus c1 plus c2 lambda plus k1 plus k2. So this term, multiplication of these terms, minus lambda 1 c1 minus lambda 1 c1 minus k1 whole square is equal to 0. So this will have like lots of terms, and it's a fourth order. It will be basically a fourth order equation. So it will have four roots. So let us say we call them as lambda 1 1, lambda 1 2, lambda 2 1, and lambda 2 2. And so these are, let us in a way, they are basically four eigenvalues. So they are not actually four eigenvalues, but you can say that I mean here lambda square is an eigenvalue as such. So there will be two natural frequencies and are basically two eigenvalues. So lambda 1 1 and lambda 1 2, all these are, they may be complex numbers. So just note that. So when you actually try to solve, like, considering some particular values of m1 c1 or k1, they actually may turn out to be complex numbers, but they are generally complex conjugates. So lambda 1 1 and lambda 1 2 will be complex conjugates, and let us say lambda 1 square and lambda 2 square. So these are the two eigenvalues which correspond to the natural frequencies of this system. So I'm just like letting you know beforehand to avoid any confusion that you might be thinking that, this is just a 2 degree of freedom system and how come we have four roots? So we have four roots which are complex conjugates, which is basically these are, when you take the square root of this thing, so we will get two roots occur, and those are lambda 1 1 and lambda 1 2. So so like this is correspond these two are corresponding to this lambda 1 square, which is again another eigenvalue. And so are you able to follow up to this part? So when you will realize this once you actually solve with proper numerical values. So let us take this. So you can take my word for now, and so you will realize this lambda 1 1 lambda 1 2 when once you solve an actual problem with numerical values. So you will actually come to know that these are complex conjugates as such. So and we will have again four vectors, so corresponding to each root lambda 1 1 we will have this vector v11. So let us say this is the corresponding, eigenvector or whatever associated with this particular root, lambda 1 1 or lambda 1 2, or so what we actually observe is that they actually come out. So the v11 and v12 they actually come out to be the same. So corresponding to each, let us say, eigen value, let us say lambda 1 square. So there will be a eigen vector, let us say v1. So so we write it separately as v11 and v12 just to like, which is the eigenvector associated with that root, but it actually comes out to be like that v11 and v12 are equal. And so this is the kind of broadly the concept. So now, uh, once you solve for these, like basically get the roots, then let us call this matrix as, so since we are already like writing it as this ax, so instead of ax, let us say call this equation now as like, uh, you know a into v is 0. So for a non-trivial solution of v, so we said that determinant of the matrix A is 0. So then, so how do we find out this v11 v12 is by basically substituting this uh, let us say lambda 1 1 square m plus lambda 1 1 c. Yeah. So we have to solve basically for this equation for each root. So we can generalize this equation as so let us call it as lambda square ij and v subscript ij. So the subscript ij can take two values like one or two, like depending on the which root are we talking about. So we will get the corresponding vector v11 or v12, whatever corresponding to that, by solving this equation, matrix equation. So so if we like for example, if we take this just take the first row of this matrix A to illustrate like this. So to illustrate this calculation, so I'll just take, let us say, one row, how to find out this eigenvector to illustrate that. So I will just take, let us say, so there are like two sets of equations, right? So set of two equations. Um, so what we have is that, so each vector Vij is essentially a set of y1 and y2 only for each, corresponding to each whatever lambda eigenvalue that we get. So so this is for the ij index. So does everyone understand this notation? So what we get is that, let us say we take the like first row of this matrix A, then so each eigenvector now, what we can write it as now? So this equation here, which I've written on the lower side, so that is in terms of this lambda ij. So for each index, we will get this some relation between y1 and y2. So y1 and y2 will be in always in a certain relation. So it will be that uh, so here let us say y2 is some expression, this lambda ij square m1 plus lambda ij c1 plus k1 whatever. This in terms of y1. So then so let us denote this whole this term whatever we which is there in this big bracket. So let us denote it as let us say some alpha. So it's basically that y2 is some alpha y1, right? So then what will be the eigen? So this alpha, let us call it as alpha ij. So it will depend on the ij index, right? So this is like some alpha ij y1. So that alpha ij will depend on the ij index or whatever whichever ijth root that we are referring to. So then now the vij vector will be basically y1 and set of y1 and y2. So it will be basically y1 and y2 we can write it as alpha ij y1, or we can take y1 outside and say it is 1 and alpha ij. So y1 here we can take it out and say that y1 can be any real number. So fundamentally it is only, so the eigenvector can be thought of. So y1 is just a scalar multiplier, you can say. So the actual vector, the smallest reduced form is fundamentally only 1 and alpha ij. So that is the eigenvector corresponding to the ijth root. So from that you will basically get the v11, v12, v21 and v22 whatever corresponding to each lambda 11, lambda 12, lambda 21 and lambda 22. And essentially they actually come out to be the same for like v11 and v12 come out to be the same, v21 and v22 actually come out to be the same, and lambda 11, lambda 12 will be complex conjugates, and lambda 21 and lambda 22 will again be complex conjugates of each other. So yeah, so I understand it may be slightly complicated, but I think once you try it on your own, this is like a very fundamental approach that you can extend it to any degree of freedom system. So it need not be only 2 degree of freedom. So it can be, any extend this approach, you can extend it to any degree of freedom system. So it is robust in that sense. So, so is it becoming too complicated? Yeah, I understand it may be slightly complicated, but yeah, so basically I'll just try to kind of, we have gone into too much of mathematics, but let us come back to the physical world now. So let me just try to kind of consolidate whatever. So we started off with this like homogeneous differential equation, and we are trying to find out the natural frequencies, which are basically eigenvalues, and the mode shapes, which are basically corresponding to the eigenvectors. So, and because this is a matrix equation, so that's why we are into this matrix algebra to derive the what are the eigenvalues and eigenvectors. So for that, I suggested that we substitute, let us say, a trial solution y is equal to v e to the power lambda t, and then we did a lot of matrix algebra too, and said that we have a characteristic equation that has four roots and the corresponding vectors that represent the eigenvectors basically. So for that corresponding eigenvalue, so that is the essentially what we get for this. So now these are the basically the eigenvalues and eigenvectors we got for the as the solutions to the homogeneous equation. So now so the homogeneous solutions to the homogeneous differential equation are the free vibrations, basically the represents the free vibrations, and we can write now the solution YH. So because the solution can be written as uh, a linear combination of eigenvectors. So let us say C11, C12, or whatever they are, like some unknown constants. So we can write it as a combination of the linear combination of the eigenvectors. So that is the uh, solution, and C11, C12, or C21 and C22 are basically unknown constants which can be found out by based on using the initial conditions. So this is our solution to the homogeneous differential equation, which is the free vibration. So if you remember for uh, you know the single degree of freedom problem, so we again had this similar way of writing this solution for the homogeneous differential equation. So if you recall, so what I told you that V11 and V12 actually come out to be the same, and lambda 11 and lambda 12 are complex conjugates. So e to the power lambda 11 and lambda e to the power lambda 12 again are like complex conjugates. So like, so then uh, this is like uh, so you can also interpret it as summation of sines and cosines. So in that sense, uh, yeah, so it basically depends on the mass and stiffness properties, what are the nature of the roots. So so these are the solution to the homogeneous equation, which is the which represents the free vibrations, and similarly we have the particular solution, uh, let us say yp, which depends on the nature of the force, uh, which is harmonic force. Let us say if it is a harmonic force, so then we can write yp as some a vector which is, let us say, a1 sine omega t plus b1 cos omega t, and a2 sin omega t. Why I have taken two things is basically because we have two differential equations. So for each mass, let us say, uh, it represents the part of the harmonic forcing that is acting on that particular mass. So the even if the harmonic force is actually applied only on one of the mass, so its effect will be eventually be transmitted to the other mass also. Let us say if there are two masses and I apply harmonic force to one of these, let us say if we look at this system here, so if we move the base with some, like, let us say E of t is some E not sine omega t, then the forces will be transmitted through the spring and damper to the mass m2, and that force will is like further transmitted to the mass m1 and m1 through the spring k1 and c1. So its effect will be felt by both the masses. So the harmonic force, so therefore the response to that harmonic force will have these two sinusoidal components as such, for each corresponding to each mass. So what we have to do to get the response, or the steady state response or response to the harmonic forcing, is we have to substitute this particular solution in the differential equation, right? So it's uh, that that means that, so what was our original differential equation? It was basically m y double dot. So instead now we substitute it in the differential equation. So we write myp double dot plus c into yp dot plus k into yp is equal to the harmonic forcing F. So we can derive the particular solution yp from this matrix equation by assuming this sinusoidal form of yp. So we can differentiate yp and find yp double dot, what is yp dot and yp, so and substitute it in the differential equations. We already know the matrices m, c and k. So from that we can find out so we can compare the coefficients on both sides. So f will have, let us say, some components, let us say f1 sine omega t, and let us say f2 cos omega t. Uh, so then we have to compare the coefficients of the sine and cos terms and equate it, like compare the coefficients and find out the values of the coefficients a1 b1 a2 b2 using the usual method, like the single degree of freedom systems. It's like in the similar way we can find out these coefficients of a1 b1 a2 b2 depending on the nature of the force, harmonic force that we apply. And uh, so we can find out a1 b1 a2 b2 basically if the force F is known. Now we have to combine the two solutions, which is the homogeneous and particular solution, and solution to the homogeneous differential equation will be the free vibrations. And now we have to apply the initial conditions now and find out the values of the coefficients using the initial conditions. So since there are four constants, so we need four initial conditions. So we basically need what is y1 of 0, y2 of 0, basically the displacements, and velocities y1 dot and y2 dot at time t equal to 0. So initial conditions meaning that we need to know what is y1 of 0, y1 dot at time t equal to 0, y2 of 0, and y2 dot at of 0. So these are the four things that we need to know to derive the unknown constants, so that we get the coefficients, and then we basically are able to find out the total response for that. So I understand it must be slightly difficult to digest, but uh, I hope that if you, I think you can later on try to listen to the recording and let me know. Maybe if you have any doubts, like you can also try to write down on your own whatever that we have gone through, uh, and let me know if you have any doubts. But yeah, so fundamentally this approach can be extended to any number of degrees of freedom. But let us say since we are discussing 2 degrees of freedom, so we can uh, restrict ourselves to the two dimensions, like basically 2 by 2 matrices, matrix equations. So my intention for going through this kind of theoretical kind of a derivation was to first introduce whatever, like give you a more like fundamental approach to solve any multi-degree of freedom systems problems, and then use like solve it analytically, and like basically to first start with the free body diagram, then derive the equations of motion, then write it in a matrix form, and so analyze it in the solution into two parts. So if it's a forced vibration problem, so it will be basically solution will have two parts: complementary function and particular integral, same as uh, the single degree of freedom thing. And so the homogeneous part will contain basically the information about the natural frequencies, and which is basically the eigenvalues and eigenvectors for that, and then the particular solution which depends on the nature of the forcing. So that's about the uh, overall approach to any multi degree of freedom system. So we can take a, yeah, yeah, it is useful for systems having, yeah, so it's like this approach, like later on if you want to extend it to a multi degree of freedom system, so you can simply extend using the same notation and whatever method that I just described. Right. So here we have a particular example, like a problem where the values of the stiffness and masses are known. So let us just first I think we may not have enough time to completely solve this problem, but at least we will try to do as much as we can. But hopefully that helps, like the earlier explanation helps you understand the general method. So here we also start with the same way we start, like, so here we the two degrees of freedom are already indicated, x1 and x2, and here the base is fixed. So then those are the two degrees of freedom here. So we will just directly draw the free body diagram of the system here. So the free body diagram of mass m1. So we'll assume that x1 and x2 are again with respect to the measured with respect to the equilibrium position. So then we'll not account for gravity. So the now since the base is fixed, so we can write that the spring force here is k1 x1 only, and here since the spring k2 both the ends are moving with respect to each other, so then the tension in the spring, let us say we can write it as k2 into x2 minus x1, let us say. So now we have the free body diagram for this, and we now can write down the equations of motion. So basically m1 x1 double dot m1 x1 double dot. So here there is no damping, so it's relatively simpler to derive the equation. Now since downward, we are assuming that downward direction is positive, so we will write it as minus k1 x1 plus k2 into x2 minus x1, and similarly for m2 x2 double dot will be equal to minus k2 x2 minus x1 because it is acting in the upward direction. So now you can rearrange the terms and write down the equation in a matrix form. So it will be So K1 plus K2 minus K2 and minus K2 and K2. So this is a free vibration problem. So that's why there is no forcing, there is no damping here. So we just have a mass matrix and stiffness matrix. So now we can use the similar method that we just uh, discussed now. So, but before that, we already know that there is some uh, relation between the masses m1, m2, k1, k2, and so we can simplify the equations slightly. So we can write it as m1 as m and m2 is 2m and k1 as k and k2 as 2k. So this will become 3k and k2 is because it is 2k, so it will be 3k minus 2k minus 2k 2k into x1 x2 is equal to 0. Now we can follow the same approach that to so if we denote this x1 and x2 vector as some capital X, let us say, and we assume that this vector capital X is, let us say, some v e to the power lambda t. Then and substitute this in the this matrix equation or differential equation, then we will get the characteristic equation. So it will be like somewhat like this. So I'm just skipping steps and you can try it. I think you will get the same thing. So you will get basically, so in the interest of time, I'm just skipping the steps in between. So we basically get this uh, equation and determine, and we have to find out the determinant of this equated to be 0. So as to find out the so we will get the fourth order equation in terms of lambda square. So which is lambda square m plus 3k into 2 lambda square m plus 2k minus 2k whole square, which is 4k square, is equal to 0. Now we have to expand this and simplify to get the fourth order equation now. So it will be basically 2 lambda to the power 4 m square. Uh, so basically you get 2 lambda to the power 4 m square plus 8 lambda square mk plus 6k square is equal to 0. And using the the values of m and k which are given, so we can solve for lambda and get the roots, four different roots, lambda 1 1 lambda 1 2 here. So here you can actually say that you can do a simple substitution, because here there is it's actually a fourth order term, a fourth order equation, but you can solve it like a quadratic one by saying that lambda square is some z, or some kind of substitution. And you can also simplify by saying that k by m is some omega square, and derive the and divide the both sides of the equation by, let us say, m square. So we will get that 2z square plus 8. So here we'll get so when we derive divide by m square, so we will get the term k by m, which is again omega square, 8 omega square z plus 6 into k square by m square, which will be omega to the power 4, or alternatively we can just say it as this is 2 lambda to the power 4, and instead of writing this as z, so now since this is, so we can simplify this further by dividing by 2 as well. So this will become 3. So this will have the roots. So I think it's a simple, like a quadratic equation. So if you can solve it as lambda square plus 3 omega square and so you can factorize it like this, right? So so you will basically get the solution as lambda. So lambda 1 square, let us say, is the first eigenvalue, is basically minus 3 omega square, and lambda 2 square is minus omega square. So omega square here meaning k by m, just it's a substitution. So let me just rewrite it properly. So you can also write it as lambda 1 1 is basically the root of lambda 1 square, because this is a complex, so omega square is positive and minus 3 is a negative number, and square root of that will be a square root of negative number will be imaginary, right? So it will be basically, so lambda 1 1 you can write it as root 3 I omega, lambda 1 2 is minus root 3 I omega. So yeah, sorry for the bad handwriting. So I is basically root of minus 1. So lambda 1 1 is root 3 I omega, lambda 1 2 will be minus root 3 I omega. So you can see that they are complex conjugates of each other. Lambda 1 1 and lambda 1 2 are complex conjugates. And uh, similarly, uh, lambda 2 1 will be I omega, and lambda 2 2 will be minus I omega. So these are the four lambda 1 1, lambda 1 2, lambda 2 1, and lambda 2 2. So these are the four roots that we were talking about, and using this we can derive the eigenvectors also. So we know the uh, basically the set of differential equations here. So let us just use the first differential equation to derive the eigenvector. So what we are essentially doing is So we have this equation, right? So in terms of x1, x2. So what we need is, so for the eigenvectors, we need, or basically the mode shape corresponding to each natural frequency. So we need to basically substitute the corresponding eigenvalue. So if we want to find out V11 corresponding to lambda 11, what we will do is we will say lambda 11 square m plus 3k x1 is equal to, or basically minus 2k x2 is equal to 0. So we get that x2 is basically lambda 11 square m plus 3k by 2k. So now what is lambda 11? It is root 3 I omega. So lambda 11 square will be 3 I square omega square. So I square is minus 1. So it will be minus 3 omega square. And omega square is k by m. So omega square into m will be k. So it will be 0. Similarly, if we substitute the value of lambda 12 square, so to get V12, so we will actually end up with the same uh, relation between x1 and x2, which is, or basically the same eigenvector. So if we substitute lambda 12 or whatever, so we will end up with the same eigenvector. So let us say V11 is equal to V12 is equal to, so since, so it's basically 10 is the, let us say, eigenvector here. So similarly, you can find out the eigenvectors like V1, V21 and V22 by substituting the eigenvalues uh, for basically the corresponding to the eigenvalues lambda 21 and lambda 22. So we will basically get the relation between x1 and x2 for corresponding to that root lambda 11 or lambda 21, whichever, and that will be the eigenvector V21 and V22. So let's try that. So let's substitute the, so lambda, So lambda 21 is I omega. So lambda 21 square will be minus omega square. So and minus m omega square will be k. So it will be minus k plus 3k x1 minus 2k x2 is equal to 0. So it will be 2k x1 is equal to 2k x2. So which is basically x1 is equal to x2. So therefore the V21 will be 1 1 because both are equal. That will be the mode shape. And similarly, if you substitute lambda 22, which is uh, minus I omega, so lambda 22 square will also be minus omega square. So it will be again the same. So you will end up with the same relation. So in that case also you will end up with basically the same eigenvector V21 and V22. Yeah, so in this I just wanted to make one correction here. So here for the first, when we substitute the first eigenvalue, here we uh, got, so I think I probably made a mistake here, but so not sure why x2 is equal to coming out to be 0, but let's try with the second row equation. So if minus 2k x1 and so lambda 11 square was uh, minus 3 lambda 11 square m is 3 lambda 1 square is 3 omega square, right? So minus 3 omega square. So here we are getting minus, yeah. So let's use the second row equation here for calculating the eigenvector for this. So we will get minus 2k x1 plus 2 lambda 11 square m plus 2k into x2 is 0, and lambda 11 square is lambda 12 square is equal to minus 3 k by m. So we basically get that x1 is equal to minus 2 minus 2x2. So our eigenvector v11 is actually 1 comma minus 2. So that is our eigenvector. So so that is the mode shape corresponding to the natural frequency, first natural frequency, and so this will come out to be same as v12 will come out to be the same thing, and v22 and v21 we already got. So this is how we can use this method that we saw for a 2 degree of freedom system. So our natural frequencies are, so basically lambda 1 square is minus 3 omega square. So our natural frequencies, let us say omega 1 will be root 3 k by m, and the second natural frequency omega 2 is same as k by m. So those are the two natural frequencies, and we this the eigenvectors that we derived are the mode shapes. So that's how we can solve these kind of problems um, using the method that we just have gone through. So that's all that I had from my side, and I think we are already over time by the usual time. So yeah, so let me know. So I would request you to go through the recording once more and try to derive this thing on your own, and do let me know if you have any questions in the next session. So we will meet. Yeah, so we will meet in the next session. So yes, Amit ji, so
Well,
yes.
would you please explain the last step? How did you get omega 1 and omega 2, sir?
So see, so what we have done here is that we have assumed the solution of the form e to the power lambda t, right? So lambda square is the kind of the magnitude of lambda square is generally the is the natural frequency. So so if we actually had assumed the solution of the form, let us say e to the power I omega t, like of that form, then whatever we get will be directly the uh, omega will be directly the natural frequency here. But now here we are getting the characteristic equation as a fourth order equation in terms of lambda, so lambda to the power 4. But now yeah, so this is basically the characteristic equation is in terms of the fourth order uh, in terms of lambda. So lambda square will be the, because it's a 2 degree of freedom system, so lambda square is the actual eigenvalue, and because this is so lambda 1 square is minus 3 omega square. So root of lambda 1 square is root 3 I omega, and lambda 2 square root of that is uh, I omega, right? So plus or minus I omega, or plus or minus root 3 I omega, right? So So the I omega part is, so when you substitute, so consider the, the let me give you an example to understand what I'm saying. So basically, so if you consider mx double dot plus kx is equal to 0, so in this equation if you substitute x is equal to some x naught e to the power I omega t as the form of the solution, so x double dot will be minus omega square x naught e to the power I omega t, right? And so then we'll write it as minus omega square m plus k into x naught e to the power I omega t is equal to 0. So this will be the form of the equation if we substitute this solution in this form. So if we had substituted it as x is equal to, now let us say take x1 e to the power omega some lambda t, let us say not omega t, let's say lambda t, and then repeat the same steps. So then x double dot will be lambda square x1 e to the power lambda t. So our equation will be like lambda square m plus k into x1 e to the power lambda t is equal to 0. So now if you compare the two equations, lambda is essentially I omega. So do you agree with this?
Yes, sir, from the last equation, sir.
Lambda is, if you substitute lambda is equal to I omega, you
Yes,
will
sir.
get, so
Yes,
you
sir.
will get back this same thing. Now from this
Ye-
we know that omega square is equal to k by m is the natural frequency, right? So similarly here, when we say lambda 1 square is equal to minus 3 omega square, so we are saying that lambda 1 root, so basically root of lambda 1 square, uh, so when we say lambda 1 1 or whatever, so we derived that lambda 1 1 is this something into root 3 I omega, right? So using the same correlation, so say, using the same logic that lambda is equal to I omega, so whatever omega part that we have, uh, so that is the natural frequency, right? So root 3 omega into I. So forget this I part. So whatever root 3 omega is representing the natural frequency, right? So that coefficient. So by using that same logic, I said that omega 1 is root 3 omega, which is k root omega, which is root k by m actually. Sorry, this should be. So this is how I actually concluded that the first natural frequency is like this root 3 k by m and root k by m. So is that okay?
Yes, sir.
Okay. Okay, fine. So then that's all that I had from my side. So we can end this session for today over here. So thank you all for joining, and good night.